Hello, this video is going to be on lesson 1.3, transformations of function graphs. Now, we began covering this on September 2nd, 2016, and what I have here is, as part of your do now, is to graph the function f of x equals x squared and g of x is equal to the square root of x. Now, this is basically from the function cycle, where you have to go from the equation into the graph. So let's point out some very important things here. Looking at the table, basically the x values are called the independent variables or the inputs, and the y is going to be the outputs. So the reason x is the independent variable is because you can pick these numbers whichever numbers you want. Basically doesn't matter what numbers you pick, but in this case we're going from -3 to 3, +3. Now, the reason we call these inputs is if we take -3 and plug it into x squared, so -3, and we square it, our output is going to be +9. Now, it's very important, when you have a negative number, you put it in parentheses before you square it, or else it's going to give you the wrong answer. Alright, so we're going to do the same thing for -2. You input it for x, -2 squared is 4, and you keep going down your list of inputs and get the corresponding output. So -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. Now, what we can do with this table that is now complete, we can go ahead and look at the ordered pairs, and these are basically xy coordinates. So we take -3, 9 and put it on our graph. -2, 4, there's the point right there. -1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. So we went from our function into a table, and from the table we can find the ordered pairs to get our graph. And so our graph, when we connect the points, is going to look like this. And by the way, this is called a parabola. The shape of this curve is a parabola. Now, let's do the same thing for the square root of x. If we plug in the square root of x, if we take our inputs from our table and plug them into the function, the square root of 1 is going to be 1. Now, this is where you may need your calculator. If we plug in 2 in for x, let's see here. Okay, here we go. So if we take 2 and we take the square root of it, it's going to be 1.41. We're just going to round it to 2 decimal places, 1.41. If we take the square root of 3, it's going to be 1.73. Now, if you take the square root of 4, that's going to be 2, and the square root of 9, our output is 3. So we don't have all whole numbers here, but we did complete the table. Now we can take the ordered pairs and put them on our xy plane. So, and there's one more input I want to include here. I want to include 0. So if I plug in 0, and so the square root of 0 is going to be 0. So we have 0, we have 1, 1, 2 and 1.41, which is somewhere around here, 3 and 1.7, 4 and 2, and then we jump to 9 and we have 3. So when we connect these points, the graph is going to look something like this. Okay, so we graphed x squared and we graphed the square root of x. Now let's focus on x squared. Here we have f of x equals x squared. Now we're going to change the function x squared by adding and subtracting different things. So if you look at all these different equations below it, we have x squared. That's the original function, but we added 5 here. Here again we have x squared, but we subtracted 5. Here we basically still have x squared, where x is there and then the squared is there. And this time x is inside parentheses where we're adding 5 right next to it. Here we're subtracting 5. Here we have x squared, and here x has a negative right next to it, but we're also squaring it. So for each of these equations below, it's basically still the function x squared, but we're doing something different to each of these. Now, when we graph each of these, so what I had you do is I had you use your calculator and graph each of these functions and tell me what exactly does each equation. There's something different about each of these functions. What is going on when we add 5 to the end of each function? So let me go ahead and pull up the calculator. Okay, so this is a calculator that we use during class. We want to use the graph. So just so you know where we're at, here's the home screen. You're going to click on this, the shape of a parabola with the graph on it. First, let's go ahead and graph x, and to square it, you use that symbol right there. So press enter, and there we have our graph, x squared. Now, what happens to the graph when we add 5 at the end? We want to see how does the graph change? Okay, so you're going to press tab. We're going to graph x squared, and this time we're going to add 5 at the end. And once you press enter, I want you to see, how does the graph change? So if you take a look at this, we have the same shape, but notice that when we added 5, the graph moved up 5 units. 1, 2, 3, 4, 5. So the way I want to write this is that it was translated up 5 units. So when we added 5, we translated up 5 units. Okay, so that's what happens whenever you add a number after the function. What if you subtract a number after the function? How is that going to change? So let's go back to our calculator. Let's go ahead and erase. You want to press tab. If we put all these functions in at the same time, it's going to get cluttered. So let's go ahead and erase that. And instead of adding 5, we're going to subtract 5. Okay, let's go ahead and press enter. And notice notice that here is our original function, x squared. When we subtract 5, notice that we went down 1, 2, 3, 4, 5 units down. So the way I want to write this is that we translated down 5 units. Okay? Okay, here we have something different. We have x plus 5 in parentheses, then we squared. So let's press tab, press up, and let's go ahead and erase this. Let's put parentheses, x plus 5, close parentheses, and then we're going to square that. Alright. I think I erased it. Yeah, I have to do this all over again. Alright. Now take careful look at what happens when I press enter. Look at that. Here's the original function, x squared. When I add 5 inside of the parentheses and I have the square on the outside, notice that the graph moved 1, 2, 3, 4, 5 units to the left. So in this case, I have it that it translated 5, translated left 5 units. Can you guess what might happen when inside the parentheses we subtract 5 units? Well, let's go ahead and figure out what happens. So let's go ahead and subtract 5 units inside of the parentheses. Take careful look at what happens once I press enter. And if you said that it's going to move to the right 5 units, you are correct. 1, 2, 3, 4, 5. So this time it translated to the right 5 units. So notice when we have addition inside the parentheses, it's moving to the left. When we have subtraction inside the parentheses, it's moving to the right. Okay, so there's some interesting things that we are seeing here for each of these different functions. Now let's take x squared and put a negative in front of it. How is that going to change the function? Well, let me press tab. Let's go up. Let's erase that. We're going to put our negative x, and then we're going to square it. Pay attention to what happens when I press enter. Again, our original function is the blue graph. How can we describe what is going on with the red graph? How do we go from the blue to the red? Well, notice that the red graph is basically flipped across the x-axis. So it's flipped across the x-axis. The x-axis acts like a mirror, and it's basically reflecting the parabola, the blue parabola. The red parabola is a mirror image of the blue parabola across the x-axis. So the way we want to write this is that it is reflected across the x-axis. Alright. And finally we have negative x squared, where the negative is inside of the parentheses. Let's go ahead and graph that. So all we have to do here is put a set of parentheses inside, let's parentheses, negative x inside the parentheses, close parentheses, and then you want to square it on the outside. Alright, let's see what happens when we press enter. What's going on here? Here's our original function. Did the graph change at all? No, it didn't. It's exactly the same graph. Now, since we said that this, if we have the negative on the outside, it's reflected across the x-axis. If the negative is on the inside, your intuition might say that it's going to be reflected across the y-axis. Is that what is going on here? Let's take a look at our original graph here. Here's our original function. This is x squared. When we graphed this, we had the negative on the inside, negative x squared. And we're thinking, well, this is a reflection across the y-axis. So here is the y-axis right here. Is the y-axis acting like a mirror where on the left side it is a mirror reflection of what is on the right side? So if you look at it, the answer is yes. The left side is a mirror reflection of what is on the right side. So this is why the parabola did not even change in any way. It actually just, this side went over to the left and the left side went over to the right. And so the parabola is actually very symmetrical along the y-axis, which is why it didn't change. But whenever we have that negative inside of the parentheses, it's going to be a reflection across the y-axis. Okay. Now, so we looked at the function x squared. Now, let's take a look at the function the square root of x. And what I'm going to do is I'm going to challenge you. Notice that here is our parent function. This is the original function, which we'll call the parent function, the square root of x. Now, what happens when we start adding something for each of these functions? Notice that each of these functions has the square root of x. Square root of x is right there, square root of x is right here. Here it is right there, there it is right there, there it is right there. So, just by looking at the equations, can we guess and see what happens to this graph if we add 5 on the inside of the square root, put a negative in front of it, add 5 at the end? By looking at the patterns that we saw here, can we guess, just by looking at the equation, how the graph is going to change? Okay, so notice that here in the first one, when we translate it up 5 units, we basically have the original function. Nothing in the function changes. All we did was add 5 to the end. So is there an equation where we see the original function where we don't change it at all and we just add 5 at the end? Well, here it is. Here's the original function, and here at the end we just add 5. So since that one was translated up, then this one is actually going to be the one that is translating up. Now translates down. Again, we took the function, we didn't do anything to it, all we did was subtract it at the end by a number. So translate it down, and I do have a typo here, I forgot to fix it. This is supposed to be negative. So when we take our original function and we just subtract a number at the end, that is going to be translated down. Alright. Now, when we translated left and right in the parabola, we basically, right next to the x, we added 5 in order to translate left, and right next to the x we subtracted 5 in order to translate to the right, and then the squared was outside. Is there something similar that we can find for the square root function? Well, notice here, right next to the x, we are adding 5, and then we have the square root on the outside. So this is actually the one that is translating to the left. And the one that's translating to the right, we have our x, and right next to it we are subtracting 5 inside the square root, and on the outside we do have that square root. So this is translating to the right. Okay, finally, if we have a reflection across the x-axis, we have that negative on the outside, and if we have reflection across the y-axis, the negative is inside the parentheses. So looking at this reflected across the x-axis, notice that here the negative is on the outside, so that is the one that represents reflection across the x-axis. And here we see the negative on the inside of the square root, so that is the one that is reflected across the y-axis. So we're seeing some patterns going on here. Even though x squared and the square root of x are completely different functions, we can see that when we translate up and down, left and right, or when we reflect it, the way we're changing the functions looks very similar. So notice that when we translate it up, the function did not change. Here we still have x squared, here we still have the square root of x. All we did was add a number at the very end. So we can actually take these words and represent it using mathematical notation. So what we did in order to translate up, we took the function. So the function, we just basically take the function and we add a number at the very end. So it can be +1, +2, +3, as long as we're adding a number, and we'll represent that with a variable k. So every time you see something like this, where we take the original function and we add a number at the end, this is going to represent translating up. When we translate it down, we have the original function, but all we did at the end was subtract a number. So we can subtract. This could have been -1, -2, -3, minus any number, and it's always going to be translating down. So every time you see f of x minus k, you know that's translating down. Alright, what about translate left? What are the similarities here? Notice we take the variable by itself, and right next to that variable we added 5, and then we took the square on the outside. Here we took our variable by itself and added 5 right next to the x, and then we took the square root. So what we're doing here is we're taking the function x, and we're taking the variable x, and we're adding a number. Now this could have been +1, +2, +3, plus any number. Now since we already used k as our variable, let's use the variable h. So we basically took x, we added any number, which we'll just represent with h, inside, and then we completed the rest of the function, where here we just had to square and here we had to take the square root. So anytime you see this setup right here, where we have f x plus h, that's, you know that you're translating towards the left. Same thing for translating to the right. We're taking our variable x, and right next to the x we are subtracting any number. Could have been -1, -2, -3, minus any number, and then we write the rest of the function. So here we have f of x minus h. Okay. Now, when going on to the next one, when we reflect it across the x-axis, we can see that we take our function and it does not change at all. All we actually did was just put a negative in front of the function. So we have the original function, and all we did was put a negative in front of it. And so whenever you see this negative f of x, this is basically representing the reflection across the x-axis. Now notice here, notice that the negative is on the inside, right next to the variable x. So we take the variable x and put a negative right next to it. And then we write the rest of the function. So here we put parentheses around it and we squared it, and here we just took the square root. So notice the difference between reflection across the x-axis, the negative is on the outside. Reflection across the y-axis, the negative is on the inside. So now we went from plain English, so translate up, translate down, all the way down to reflection across the y-axis, and we wrote the mathematical notation for each of these. Alright. So this is the mathematical notation. Every time you see it, you should know that this one translates up, this one translates down, and going down. So we went from plain English into the mathematical notation. Now, notice that we can actually take our parabola and we can translate it up and move it to the left. So we can take our function and not just move it up and down or just left and right. We can move it up and move it right, or move it down and move it left. So we can use a combination of these transformations in order to move it anywhere on the xy plane. So take a look at this first one. So our parent function is x squared. Now notice here, we're taking the variable and we are adding 5 right next to it. Going back to our chart here, which one of these has where we take our variable and we add a number right next to it? Well, it's this one right here. And this one lets us know that we are translating left. So we're translating left specifically by 5 units. So we're translating, we're using the past tense here, translated left 5 units. But notice at the end we are adding 5, and so what this is which of these shows that after we wrote the function we're adding a number? Well, it's going to be this one. We're translating up. So we're translating to the left 5 units and up 5 units. So there's a different combinations of transformations. There's not just one single transformation that can occur. There can be a combination of transformations. Same thing here. Here we're translating, it's translated to the right 5 units and down, or actually it's still positive 5, so up 5 units. Alright. Now, what I had you do during class is actually create a foldable, and when this is basically a foldable that when you open it up, I had those 6 transformations that we just went over. We went over 6 transformations and basically wrote them on the first 6 rectangles. So when you open up these are basically flaps. When you open up the flap under this, f of x plus k, what I had you do is write translated up k units. So this falls directly under f of x plus k, and on the other one I had you write translated down k units. Now this is on the inside, so this is when you close it up, and this is when you open it up. Now on the side here I had you write those 2 examples that we went over. So here's x squared plus 5, and the other one that we use as an example is square root of x plus 5. Here we had x squared minus 5, and here we have the square root of x minus 5. Now continuing on, here we have f of x plus h. We said that that one is translated to the left h units. And the 2 examples that we used here were x plus 5 squared, and the other example that we had was x plus 5, the square root of x plus 5. Now the other one, f of x minus h, we said that that is translated to the right h units. And our 2 examples here were x minus 5 squared and the square root of x minus 5. Continuing on, we have negative f of x, and we said that was reflected across the x axis, and our 2 examples were negative x squared and negative square root of x, where the negative is on the outside. The other one was reflected across the y-axis, and this time our 2 examples had the negative inside the parentheses and inside the square root. Okay, so that completed just a portion of our foldables. Now we do have 2 other ones that we need to discover. So we took our function, we moved it up, down, left, and right, and we also reflected it. What might you think the other 2 transformations might be? Now, one very intuitive guess that I really liked from one of my students, is that it might be a rotation. That is a very good guess, but unfortunately that's not what that's not one of our transformations that goes in here, but it was a very good guess. So in order to discover what those other transformations might be, we're just going to quickly graph x squared. So we already did this, and when we completed the table, we basically had as our outputs 9, 4, 1, 0, 1, 4, 9, and when we graph these points, we basically get the parent function x squared. So when we connect these points, our function looks like this. Now, here's what we want to look at. So we looked at the function when we added a number, when we subtracted a number, when we added and subtracted right next to the variable x, and when we put a negative on the inside and on the outside. What is going to happen when I multiply a number right in front of the function? Well, let's go ahead and take a look. Here, so this table we used for the function x squared, which we did pretty quick because we already did it before. This table we're going to use to figure out the ordered pairs for 2x squared. So we're going to take our input of -3, plug it in for x, and that's basically 2 -3 squared. -3 squared is 9, so we have 2 times 9, which is 18. So we basically took this number and multiplied it by 2. So here we're going to take 2 squared. We're going to take -2, plug it in for x, and that's going to be -2 squared, and we're multiplying it 2 by 2 in the front. So -2 squared is 4. 4 times 2, which is 8. Okay, so when we take the rest of our inputs, here it's going to be 2, this is going to be 0, 2, 8, and 18. Now let's go ahead and take these points and put them on our graph. So now our xy plane doesn't go as far as 18, so we're going to go and start here. -2, 8 right there. -1, 2 is right here. 0, 0, 1, 2, 2, 8. Now, when we connect these points, take a look at what happens here. And I want you to ask yourself, are these graphs exactly the same? The answer is no. So, the orange one is x squared, and the red graph is 2x squared. So when we took our function and we multiplied it by 2 at the in front of the function, what happened to the function? Well, what one of my students said, it got skinnier. Yes. So let's go ahead and let me see if I can create a parabola here. No, it doesn't look like I can. Let me just create this parabola. Okay, so it looks like that. Alright, so let's say this is our original parabola. And it looks more like that, okay. So here's my parent function. The black curve is x squared. How do I go from my original function into the function that is skinnier? Well, take a look at what I do here. if I'm taking this function and I begin to stretch it vertically, when I'm stretching it vertically, what is happening to the graph? Well, it's just like what one of my students said. It's getting thinner or skinnier. And so notice how I'm stretching this graph vertically. The function gets skinnier. And that's what happens when I multiply it by 2 at the front of the function. What if I multiply it by 10 instead of 2? What do you think might happen to the graph even more? Well, it's going to get even, using your intuition, it's going to get even more skinnier or thinner. It's going to get narrower. So the graph is actually going to look something like this. And so, using the example that I just was showing you, what is going on is that we're taking this function and we're stretching it vertically. So as I'm stretching it vertically, it's getting thinner and thinner and thinner. Okay, so that is going to lead us to our next transformation. So what I did is I took x squared, which is my original function, and I multiplied by a number that has to be larger than 1. I could have also taken the square root of x and multiplied by a number in front of it. Now this could have been any number larger than 1, such as 2, 3, 4, 5, 6. So we took our function and, well, we already used k, we already used h. So this time I'm going to use a as my variable. A is going to represent any function, any number in front of the function. Now, inside, now is it always going to be a vertical stretch? Well, here we multiply, right in front of the function we multiplied by 2. Really quick, let's see what happens when we multiply it by a number smaller than 1 between, let's say this number is going to be between 0 and 1. So what happens when I take a number between 0 and 1 and put it in front of the function? Now, the way we can represent this here is by using an inequality like this, where a represents any number between 0 and 1. So in this case, we use 1/2. Okay, so again, we have our original function x squared, where this is 9, 4, 1, 0, 1, 4, 9, and the function is basically the parabola, which is somewhere around there. It's not perfect, but you get the basic idea. This is the function x squared. Now, what happens when I have a fraction in front of it? Basically a decimal between, or a fraction, or a number between 0 and 1. So let's go ahead and take each of these inputs and plug it in for x. So we have 3 squared, which is basically 9. 9 times 1/2 is basically 4.5. Negative 2 squared as our input is going to be 4 divided by 2, which is 2. Negative 1 squared, which is 1, divided by 2, which is 0.5. And basically it repeats on the other side. Okay, so let's go ahead and take these points and plot them here. So we have negative 3 and 4.5, which is here. We have negative 2 and 2, 0, 0. Oh, we also had negative 1 and 0.5, 1.5, 2 and 2, and 3 and 4.5. Now let's go ahead and connect these dots together. And take a look at the function now. First of all, are these the same? No. How are these two graphs different? So the original one is x squared. The purple graph is 1/2 x squared. If we took a look at the last example, when we increased the number, the graph got skinnier or narrower. If we take a number between 0 and 1, the function gets wider. So how would I go from the parent function into this other wider function? So let me take this function right there and take a look at what happens when I stretch it vertically. It gets thinner, but when I do a vertical compression, take a look at what happens to the function. It gets wider. So vertical stretch, it gets thinner. A vertical compression, it gets wider and wider. So those are the two fundamental ideas that we're looking at here. Let's go back to our foldable, and I think I zoomed in too much. Right on the inside here on this rectangle, we're gonna write a significant amount of information. So we want to divide this into two parts. Whenever we multiply the function where we have a number in front of the function, if the number in front of the function is, if a is greater than 1, we saw that the function gets thinner, and I showed you that it is actually a vertical I want to make sure I spell this correct. Yes, it's a vertical stretch by a factor of a. And then we saw that if a is between 0 and 1, it is a vertical compression by a factor of a. Okay, so my writing's a little bit sloppy there, but basically, let me give you a better handwriting of that. Here we go. So this is what you need to write down. For whenever we have a in front of the function f of x, if a is going to be larger than 1, so we use 2 as our example, we saw that the graph got thinner, and so it's a vertical stretch. For the other one, if we use a number between 0 and 1, in our example we use 1/2, it is a vertical compression by a factor of a. Now the other transformation, I'm going to leave it up to you to discover, but basically, let me zoom out here. So that's what we wrote down. Now what I want you to write as our two examples, the first one was 2x squared, that was the first example, and then our compression was 1/2 x squared. So that was discovering vertical stretch and vertical compression. Now the other one that you're going to be discovering is when we take a number on the where we, instead of having the a on the outside, we put a on the inside of the parentheses right next to the x. So we're taking a x and multiplying by a first. And so the two examples that we use here are 2x squared and then 1/2 x squared. And so when you go through these, I want you to go through these individually. Take a look at what happens to the graph. And for the sake of time, what happens is that if a is larger than 1, so our example was 2a, 2x, and then we square it, we get a horizontal compression factor of 1/a. And if a is between 0 and 1, we get a horizontal stretch factor of a. So I leave that up to you as an exercise to discover why is it called a horizontal compression and why is it called a horizontal stretch. So in order to figure out why it is called that, take a look at these two examples. We already know what these are: 9, 4, 1, 0, 1, 4, 2, 4, 9. Figure out what are the values that go here, and then figure out why is this called a horizontal compression. Why is it called a horizontal compression? And then take a look at this. We already know that this is 9, 4, 1, 0, 1, 4, 9. And then you're taking this function and filling in this table, plot the points, and ask, why is this called a horizontal stretch? Okay, so that is an exercise up to you to discover on your own. Alright. So here is our complete foldable, and then on the inside it should look like this. This right here, what goes here is basically this right here. Alright. Thank you for watching.